Welcome to the Data Communications Training Classroom. Today, let's talk about some of the basic principles of IP routing, including route selection rules, static routes, and route summarization. First, let's talk about route selection rules. Routing is a fundamental concept on IP networks. IP networks enable nodes to communicate with each other by exchanging data, which relies on network devices for transmission. Each router maintains a routing table locally, which contains routing entries learned by the router. Each routing entry is called a route. A route consists of several elements, including a prefix, destination network and mask length, outbound interface or next hop IP address, priority, and cost. The routing table is also called Routing Information Base, or RIB for short. It works a bit like a map and is necessary for each router to implement data forwarding. When the router or another Layer 3 device receives an IP packet, it obtains the destination IP address from the IP header of the packet. The router then searches its routing table for the routing entry that best matches the destination IP address. It forwards the packet out of the outbound interface mapped to the best fit next hop IP address in the routing entry. This process is called routing. If no route matches the destination IP address, the router discards the IP packet and sends an ICMP unreachable packet to the source IP address of the IP packet. A router discovers possible routes to network segments, selects the optimal route to each network segment, and adds the optimal routes to its routing table. The router maintains the routes in its routing table and forwards data packets based on the routes. A router uses routing protocols to obtain routes. Before routing protocols are enabled, the router knows only the routes to directly connected network segments. In the network shown on the screen, an IP address of 192.168.1.1/24 is configured for interface GE 0/0/0. The network segment of 192.168.1.1/24 is 192.168.1.0/24. When the physical status and protocol status of GE 0/0/0 are both up, a director route is automatically generated and added to the routing table. The physical status and the protocol status indicate whether the interface is working normally. If the physical status is up, the interface is properly connected to a link and is receiving voltage signals normally. If the protocol status is up, the protocol enabled on the interface is running normally. For example, Layer 3 interfaces run an IP protocol stack. If the IP protocol stack is up, the protocol status is up. In most cases, after an IP address is configured for a Layer 3 Ethernet interface, the protocol status of the interface goes up. Sometimes we need to deactivate an interface temporarily for testing purposes. For example, after we run the shutdown command, the interface goes down, and the director route on the interface becomes unavailable. When the test is finished, the interface must be re-enabled using the undo shutdown command. Otherwise, the director route on the interface will remain unavailable. Each root in the routing table includes the following fields. Root prefix. A root prefix consists of two parts, the network segment ID and the mask length. Both parts are indispensable. For example, though the two roots 192.168.1.0/24 and 192.168.1.0/25 both reside on the network segment 192.168.1.0, they are still two different roots because they have different mask lengths. Protocol. The protocol indicates how the root was obtained through a directly connected network segment. Static root configuration, or a dynamic routing protocol, such as OSPF, is, or BGP. Priority. When multiple routing protocols run on the device and they discover multiple routes to the same destination, the priorities specified for the protocols are used for route selection. The route discovered by the protocol with the highest priority, smallest priority value is selected for IP packet forwarding. Cost. The cost of direct and static routes is 0. The costs of the routes learned through dynamic routing protocols vary depending on the specific situation. Flags. If D is displayed in the flags field, the route has been delivered to the underlying fib. The next hop and interface fields indicate the next hop IP address and outbound interface, respectively, and are used to forward packets that match the root prefix of the route. Routes are obtained using three methods. They can be automatically generated through network segments directly connected to interfaces, as long as the physical status and protocol status of the interfaces are both up. They can be manually configured by network administrators as required. They can be discovered by dynamic routing protocols. Let's use ENSP for this example. First, let's establish a network that consists of three routers, AR1, AR2, and AR3. GE 0/0/0 on AR1 is connected to GE 0/0/0 on AR2, and GE 0/0/1 on AR2 is connected to GE 0/0/0 on AR3. Bear in mind that we need to use GE interfaces instead of Ethernet interfaces, because Ethernet interfaces are Layer 2 interfaces that do not need IP addresses. Suppose the IP addresses planned for GE 0/0/0 on AR1, GE 0/0/0 on AR2, GE 0/0/1 on AR2, and GE 0/0/0 on AR3 are 192.168.12.1/24, 192.168.12.2/24, 192.168.23.2/24, and 192.168.23.3/24, respectively. These IP addresses are planned according to a rule to help with modernization. Specifically, the 2 digits in the third byte of each IP address are a set of numbers of interconnected devices, and the digit in the fourth byte is the device number. For example, the 2 digits in the third byte of 192.168.12.1/24 are 1, 2, which is a set of device numbers 1 and 2, corresponding to AR1 and AR2. The digit in the fourth byte is 1, which indicates AR1. Now let's configure system names for the routers. What we need to do is to double-click the icon of each router and set the system names for AR1, AR2, and AR3 to R1, R2, and R3, respectively. We then need to configure the planned IP addresses for the interfaces using the IP address command in the interface view. After the IP addresses are configured, we can check connectivity using ping. It turns out that R1 can ping R2 and R2 can ping R3. We can run the display IP routing table command to check routing information on each device. Let's use R1 as an example. We find that multiple routes exist in the routing table of R1, among which the route 192.168.12.0/24 is a route to the directly connected network segment of GE0/0/0. If we run the shutdown command on GE0/0/0 on R1, we find that the route 192.168.12.0/24 disappears from the routing table. Let's check whether GE0/0/0 is down. In this case, we can run the display IP interface brief command, which is used to check brief information about all interfaces. In the command output, we can find that both the physical and protocol status of GE0/0/0 is down. Now let's activate GE0/0/0 to check whether the director route can be restored. We find that after we run the undo shutdown command, GE0/0/0 goes up, and its director route appears again in the routing table. We have learned that R1 can ping R2 and R2 can ping R3. Can R1 ping R3? Let's have a try. We find that R1 fails to ping R3. This is because R1 does not have a route to the network segment 192.168.23.0/24. Without such a route, packets cannot be sent to R3. One simple solution to this problem is to configure static routes. In this network, R2 is connected to the network segment 192.168.100.0/24, and R3 is connected to the network segment 192.168.200.0/24. If the PC wants to access the two network segments, it sends packets to its gateway, R1. However, R1 has routes only to its directly connected network segments. In this case, we can configure two static routes by specifying the outbound interface and next hop IP address to tell R1 how to forward the packets. Static routes are easy to configure and use. However, each network segment requires one static route. If a large number of network segments exist, the workload of configuring static routes is extremely heavy. Because of this, static routes are usually used on small networks. In addition, static routes do not respond to dynamic topology changes. For example, if the network segment 192.168.100.0/24 becomes unreachable, R1 is not aware of it and keeps sending packets to R2. As a result, packets will be lost. Now let's talk about how to configure a static route. What you need to do is run the IP route static IP address mask length command In the system view, you can choose to specify a next hop IP address, an outbound interface, or both. Take the network we have already established as an example. R1 needs a static route to access R3. In this case, we can configure one using the IP route static command. In the command, we need to set the destination IP address to 192.168.23.0, the mask length to 24, and the next hop IP address to 192.168.12.2, which is the IP address of an interface on R2. After the static route is configured, we can check it in the routing table. As expected, it is displayed in the routing table. With a static route available, can R1 ping R3? Let's have a try. We find that R1 once again fails to ping R3. This is because communication requires round-trip routes. With the static route configured, R1's packet can reach R3, but R3 has no route back to R1. As a result, R3 cannot send a response to R1. To address this problem, we need to configure for R3 a static route destined for R1 with R2 as the next hop. Once this route is configured, R1 can ping R3. There are 2 points we need to bear in mind. First, communication requires round-trip routes, as we have just seen. Second, packets are forwarded hop by hop. Each hop along the forwarding path must have a route to the destination. In this network, R2 is connected to a large number of network segments. If R1 stores one static route to each network segment in the routing table, the routing table will consume excessive system resources. In addition, R1 needs to maintain its routing table dynamically, which further consumes resources. To address this problem, we need to streamline the routing table as much as possible without interrupting communication. In this example, R1 does not need so many specific routes, since it has only one outbound interface. In this case, we can configure a default route for R1 with R2 as the next hop. A default route is a static route with a destination IP address 0.0.0.0 and a mask 0.0.0.0.0. This can also be represented as 0.0.0/0. Default routes can match any IP addresses. The local device depends on the default gateway or the next hop of the default route for the packet forwarding. If the destination address of a packet matches a non-default route in the routing table of a device, the device forwards the packet along the non-default route. If the destination address does not match any non-default route, the device forwards the packet along the default route. If the destination address does not match any non-default route and no default route is available, the device discards the packet. Next, let's talk about common commands used for troubleshooting and information query. The ping command is used to test network connectivity. It displays only the connectivity of the route to the destination node without returning results for individual hops along the route. The tracer command is used to test the reachability of each node along the path to the destination node. Let's go back to our networking diagram and run the command on R1 to test the reachability of the path to R3. As we can see from the command output, the path has 2 hops. The first hop is 192.168.12.2, and the second hop is 192.168.23.3. Regardless of how many hops exist along the path, they are all displayed in the command output. The ping and the tracer commands are used for troubleshooting purposes. Next, we will talk about two commands for information query. To check the routing table, run the display IP routing table command. To check brief interface information, run the display IP interface brief command. Now, let's add two PCs to the network. The IP address of PC1 is 192.168.1.1/24, and its gateway is 192.168.1.254. The IP address of PC2 is 192.168.2.1/24, and its gateway is 192.168.2.254. PC1 needs to communicate with PC2. First, let's check whether PC1 can ping R1. The ping succeeds. Can PC1 ping R2? Let's have a try. The ping fails. Because R2 has no route to PC1, this means that PC1 cannot ping R3 or PC2 either. To allow PC1's packet to reach PC2, each hop along the path must have a route to PC2. However, R2 and R3 do not have such a route. Therefore, we need to configure a route for R1, with R2 as the next hop, and another route for R2, with R3 as the next hop. As we have mentioned, communication is bidirectional and requires round-trip routes. R3 and R2 lack a route to PC1. We therefore also need to configure a route for R3, with R2 as the next hop, and another route for R2, with R1 as the next hop. Now, let's check whether PC1 can ping PC2. As we can see, the ping succeeds. In the previous experiment, R1 used an extra interface to connect to PC1. If R1 does not have such an interface and we still need to conduct that experiment, we can configure a loopback interface on R1. Loopback interfaces are a type of logical interface. We can configure multiple loopback interfaces on the device. Let's configure a loopback interface for R2 using the interface loopback command. We can enter a question mark in the command to check the range of the interface number. As we can see, the value range is 0 to 1023. This means that we can configure a maximum of 1024 loopback interfaces. We use loopback interface 0 as an example and configure an IP address 172.16.1.1/24 for it. We can then run the display IP interface brief command to check the configuration of the loopback interface. If we need R1 to ping the loopback interface on R2, R1 needs a route. First, let's check the existing routes on R1 using the display IP routing table command. The routing table shows many routes, including dynamic ones. To view only static routes, run the display IP routing table protocol static command. The command output shows that R1 already has 2 static routes. If we configure one more, R1 will have 3 static routes. In practice, R1 does not necessarily need so many static routes. In this case, we can delete the 2 existing static routes using the undo IP route static command and configure one default route using the IP route static command with 192.168.12.2 as the next hop IP address. We can then check the default route in the routing table. Now, let's check whether R1 can ping the loopback interface on R2. The ping succeeds. In the previous experiment, the loopback interface was used to stimulate a direct network segment. Loopback interfaces can also be used for other purposes. Loopback interfaces never go down unless the shutdown command is run on them. Due to their high reliability, Loopback interfaces can be used for device management. In addition, IP addresses of loopback interfaces can be used as a router IDs for some protocols, such as OSPF, BGP, and MPLS. Last but not least, IP addresses of loopback interfaces can be used as source IP addresses of SNMP trap messages. As we have seen, a default route can reduce the number of routes that a device has to store in its routing table. However, the default route has a coarse granularity, meaning that it cannot guide traffic forwarding precisely. Route summarization offers a solution. In this network, R2 is connected to 3 network segments. If we use the static route solution, 3 static routes must be configured. Let's take a closer look at the 3 network segments. We can see that they have something in common. They all belong to the network segment 172.16.0.0/16. In this case, we can configure a summary route 172.16.0.0/16 with R2 as the next hop. This route tells R1 to forward packets destined for the 3 network segments to R2. If we use the summary route solution, R1 has to store only one route in its routing table. In this network, R1 and R3 are connected to multiple network segments under 172.16.0.0/16. If we configure a summary route 172.16.0.0/16 for R2 with R1 as the next hop, and R2 receives a packet destined for 172.16.32.0/24, R2 will use this summary route to forward the packet to R1. This is because the summary route 172.16.0.0/16 covers too many specific network segments, including those on the R3 side. In this case, we need summary routes with a finer granularity. For example, we can configure a summary route 172.16.0.0/19 with R1 as the next hop, and another one 172.16.32.0/19 with R3 as the next hop. Now let's talk about how the 2 summary routes are calculated. Suppose there are specific routes within the range 172.16.1.0/24 to 172.16.31.0/24. To calculate a summary route of the finest granularity, we need to convert the decimal notation of the start and end IP addresses 172.16.1.0/24 and 172.16.31.0/24 to the binary format, and calculate how many beginning bits are the same in the 2 IP addresses. The first 2 bytes of the 2 IP addresses are the same, and the mask length is 24, so we need to focus on the 3rd byte. As you can see from the diagram on the screen, the bits to the left of the red dotted line are the same, and there are 19 bits in total. In this situation, we can determine the summary route. Set the first 2 bytes to 172 and 16, the other 2 bytes to zeros, and the mask length to 19. We get the summary route 172.16.0.0/19. That's all for today. Thanks for listening.